So now we've dealt with radical expressions and radical functions. So the only thing that's left, of course, is your radical equations, right? Because generally we're dealing with the three things: expressions, equations, and functions, right? So radical equations are equations where the variable is part of the radicand, okay? So you're going to have a radical sign, right, somewhere in the equation, and the variable has to be part of the radicand, okay? And then I give you the little four-step process for solving radical equations, which is a little bit similar to absolute value equations that we had done in the first unit. You had to first isolate, right? So isolate the radical, whatever the radical is, isolate it, get it by itself, and then what you have to do after you isolate the radical is raise each side of the equation to a power, right? That undoes the root, right? So if it's a square root, you're going to raise each side of the equation to the second power, because squaring will undo square rooting, right? If it's a cube root, you're going to cube each side of the equation, because cubing would undo cube rooting, and so on and so forth. And when you do that, that'll eliminate the radical sign, okay? So when you do that, the radical sign is now gone, and then what you're going to end up with is either a linear or a quadratic equation, and then you just solve that normally. But again, as with the rational equations that we did in the last unit, you must check your solutions, because you could end up with extraneous solutions, as we did in the last chapter with the rational equations, right? So you always have to make sure that you check at the end. And what's important to note when you do a check is when you see that radical sign, right, that square root sign, it's assumed that you're asking for the principal square root, right, the positive square root only, okay? And that's an important thing to note when you're doing a check later on, okay? And then, of course, the important thing to note again is that you don't square until the radical is isolated, right? You got to make sure you isolate first before you square or cube. I mean, generally this is going to be squaring, but occasionally, you know, it's cubing, or even, you know, raising to the fourth power if you have a fourth root, okay? So, and then I give another little note, right? There's a lot of little notes here in my in my handouts that sometimes you have to square twice, right? If there's two radicals, for example, you might have to square once to eliminate one radical, and then square again to eliminate a second radical. All right. So I give you a couple examples there. I mean, the one on the left is fairly straightforward. When I say isolate the radical, I mean isolate this, right? So what do I do here? I subtract 3, and then I divide by 2. And once I reach this step here, my radical is now isolated. So I've isolated a square root. So to undo a square root, I would square both sides. So then what happens, like at this step here, is you're thinking almost of this square and this square root is kind of canceling out, and then you just end up with x minus 4, and then you would just add 4 to both sides to solve it, right? And then the other one, similar. What you're doing is you're isolating this radical, so all you had to do there was subtract 2. Now the issue was, once you square both sides here, sure, on the left side it's nice because the square and the square root just cancel out, but on the right side you have to actually square a whole binomial, x minus 2, so this actually required FOIL, right? You were foiling there to get from x minus 2 squared down to x squared minus 4x plus 4. And then, of course, now you have a quadratic, right? The difference between this left-hand one and the right-hand one is the left-hand one I had a linear equation, which was a lot easier to solve. Just add 4 and I'm done. Whereas the right-hand side, it's a quadratic, so you've got to set it equal to 0, and then you got to factor. All right, so I ended up with two solutions here, x equals 5 and x equals 1. But, that's why I wrote the word but there. What happens here is this. Let's do a check. If you do a check and you say, all right, the square root of 2 times 5 minus 1 plus 2, does that equal 5? Well, this is the square root of 9 plus 2 equals 5. So this is 3 plus 2 equals 5. So it's 5 equals 5. So that one checks. So 5 is good. 5 works. But then if I check 1, let's see what happens. The square root of 2 times 1 minus 1 plus 2 equals now 1. So this is the square root of 2 minus 1, which is the square root of 1, plus 2 equals 1. So this is actually 1 plus 2 equals 1. Nope, 3 does not equal 1. That doesn't work. So 1 here I would cross out, because 1 was an extraneous solution. Right? And again, remember what extraneous means? Sure, it was a solution to this equation. However, it was not a solution to the original equation. Right? And that's why you must always check back in the original equation. Okay? So in that case, you just get a solution of x equals 5, because 1 was extraneous. Alright? And then these examples here, A and B, I'm going to ask you these as the pre-class quiz questions, as 2 of the pre-class quiz questions anyway, so I'm not going to do those. Just note that in part B here, in example B, there's a cube root, so to undo that, you're not going to square, you're actually going to cube, right? So those will be pre-class quiz questions. And then of course, the last one I will do because it's a little tricky. This is one of those ones that I was noting earlier, that sometimes you have to square twice, right? Because what a lot of people will do with this equation is they'll do this. They'll say, all right, I got all the radicals on one side, so let's just square both sides. But no, that's not going to work, right? Because if you remember, what is the first step in all these square root equations? The first step in all these square root equations is to isolate the radical. And of course the problem here is there's 2 radicals, so you can't isolate them both at the same time, so I could isolate just one. So let's say I first want to isolate this one. So how would I get rid of the negative square root of x minus 6? Just add the square root of x minus 6 to both sides. Right? So I would end up with then square root of x plus 1, so that's now isolated, equals 1 plus the square root of x minus 6. So now I can square, right? Because now I have one radical isolated, so I can square both sides. But what's the problem here? The problem is, sure, the left is easy, because the square of a square root, it just undoes it. So you have x plus 1, right? You end up with the radicand. But now on the right side, 1 plus the square root of x minus 6 squared, that's actually a binomial squared. And remember what a binomial squared was? It was actually a squared plus 2ab plus b squared. Right? I'm not going to write the whole thing out. I'm just going to use this formula here. I mean, you can verify, if you want to write it out, that it's going to work. But a in this case is 1, and b is the square root of x minus 6. So a squared is still 1. And now I have plus 2 times a times b times 1 times the square root of x minus 6. So 2 times 1 is just 2 times the square root of x minus 6. And then I add this to b squared. So if b is the square root of x minus 6, b squared, it just comes out of the radical. And it's really just x minus 6. Right? The square of a square root is just whatever the radicand was originally. So I have x plus 1 equals, and now 1 minus 6 right here, right? 1 plus x minus 6 is just going to be x minus 5 plus 2 radical x minus 6. And again, now I only have one radical left. So now that's the radical I now want to isolate. So at this point, I would realize, hey, I've got an x on both sides, so they're just going to cancel each other out. And now I would have to add 5 to both sides, right? So I would end up with 6 equals 2 radical x minus 6. And since I'm still isolating this, How do I get rid of that 2? I just divide. So that's now 3 equals the square root of x minus 6. And now, finally, after much ado, I can square both sides because I've isolated that second radical. And on the right side, it's simple. They just cancel out, right? Square and square root cancel out. So I have x minus 6. And on the left side, 3 squared is 9. And now I would just add 6 to both sides, so I would end up with x equals 15. Right? So that would be my possible solution, I'll call it, right? And now I just make sure I do a check to make sure it's not extraneous. So when I do the square root of 15 plus 1 minus the square root of 15 minus 6, is that equal to 1? Well, let's say square root of 16 minus the square root of 9 equals 1. Square root of 16 is 4. Square root of 9 is 3. So 4 minus 3 does actually equal 1. So it works. So 15 actually is my solution there. So yeah, that's kind of a complicated, somewhat messy problem. And again, the reason it is because there's 2 radicals and they both must be isolated separately and squared. So you had a little bit of an issue there squaring the binomial that contained a radical. But if you follow the process, you should be okay. And then just briefly, the final thing in this section with radical equations, and you might say, oh, well, what does this have to do with radical equations? Really, it really has to do more with actually taking square roots, right? But it's really the same process as before, because remember the idea of solving equations is inverse operations, right? The opposite. So you're trying to undo whatever's being done. So with those radical equations, right, square root equations, we would square to get rid of the square root. If it was a cube root equation, we would cube to get rid of the cube root. So here you have equations of the form x to a power equals some constant k, right, some number k. How would you solve for x? You just undo the nth power. So what's the opposite of the nth power? It would be the nth root. Okay? And of course, the thing to remember, and this is important, is if you're taking in an equation an even root, like a square root, a fourth root, a sixth root, so on and so forth, you have to consider both the principal, right, the positive, and the negative root. Okay, so just keep that in mind. That's important. So if you end up with, if you have like, x to the second, x to the fourth, x to the sixth, when you take the root, you've got to take the positive or negative root. Okay, so if you look at this equation A here, it's already in that form, right? It's something to a power equals a constant. So how would I solve it? I would just take the nth root, which in this case is the second root, right, the square root. So to solve this equation here, A, I would just take the square root of both sides. But again, I took an even root here. So I know that this thing here, 3x minus 6, must be equal to not just the square root of 25, but the positive or negative square root of 25. Which means that I really have 2 equations here, right? I have 3x minus 6 equals the square root of 25, which is 5, or I have 3x minus 6 equals the negative square root of 25, which is going to be negative 5. Right? So I have both these equations here, and I just solve them separately, right? So both cases is going to be the same. You add 6 and you divide by 3. So here I would have 3x equals 11. So x is actually going to be 11 over 3. And then here, when I add 6, I'd have 3x equals 1. And then when I divide by 3, I would have x equals 1/3. Right? So in this case here, I have my 2 solutions. X equals 11/3, or x equals 1/3. Okay? And really the reason that you're breaking this up into 2 equations here is that, remember what we did. What is the square root of x squared? It's not just x. Remember, it was actually the absolute value of x. And do you remember what we did to solve an absolute value equation? What did we do? we actually broke it up into two equations, right? One where x equaled the positive value, and one where x equaled the negative value. So that's really the reason why you're breaking this up into two equations here, is that it's really, an absolute value of x and not just an x. Okay. Now, do you need to remember that? Not necessarily. It's just a matter of remembering that when you take the even root, you got to do the positive or the negative. Okay. And now the second one here, b, a little bit different because you have to isolate first, right? I tell you these equations have to be of the form x to the n equals k, and here you actually have some number times x to the n equals k. So I got to get rid of that number first, right? So bottom line is, before you solve this, you're going to have to isolate this, and then you'll take the fifth root. But after you take the fifth root, you won't have to do positive or negative because it's not an even root, right? It's going to be an odd root. Alright, so here, to get rid of this half, I would just multiply on both sides by 2. So I would end up with, that cancels, so I have x minus 1 to the fifth equals 16 times 2, which is just 32. And now again, now I have my x to the n, right? This is something to the fifth power equals 32. So to undo that fifth power, I will take the fifth root. And of course I made this come out nicely for you, right? The fifth root of x minus 1 to the fifth is just x minus 1. However, the fifth root of 32 is actually just 2, right? Because 2 to the fifth is 32. So just add 1, and I would have x equals 3, and that would be my single solution here. Okay? X equals 3 is the only real solution to that equation. Alright? And that one might actually be worthwhile to do a little graph of, just to take a look at it. Right? If you have 1/2, right? Because remember how to solve graphically? You just make one side y1 and the other side y2. So if I have a half times x minus 1 to the fifth power as my y1, and then I have 16 as my y2, just make sure when I make my window, I make y go high enough to see. Right? So make my y go to 20 instead of just 10, because I have to go to as high as 16 at least. So now if I graph this, the first graph was my half times x minus 1 to the fifth, and then of course that horizontal line is just y equals 16. So if I just find this intersection point on the calculator, I can see that it is actually 3, right? X equals 3. So that was my solution. So what did I do there? I just did a graphical check. I mean, of course, you could do a numerical check also just by going to the table and seeing where y1 and y2 are equal, and they're both equal there at 3. Okay. So that was kind of just like a little add-on to that section, right? This idea of x to the n equaling a number. Just take the nth root of both sides.